Let us look at a solar photovoltaic system. A full-fledged solar photovoltaic system contains many parts. The photovoltaic modules, power converters, and power converters for energy storage, the storage mechanisms, and the loads themselves are important aspects in any solar photovoltaic systems. We need to understand and study each of them clearly so that we will be able to design and implement each of the subsystems. We shall look at the entire generic solar photovoltaic system first, try to get an idea, visualize how it looks, and then go on into each of the subsystem, try to understand them, and then we shall design them too. One of the important players of the solar PV system is the solar energy, the sun, which is a very important component in the sense that it is the giver of the energy, it is the source of the energy. And this energy is incident on a collector, which is the photovoltaic module. So the photovoltaic module collects the solar energy and then makes available in the form of an electrical energy across the terminals of the PV module. So it is a collector and a converter which converts solar energy into electrical form. The electrical energy, one of the things that can be done to it is store it. So we pass it through a power electronic block. It is an energy charger block. It contains power electronic components like the BJTs, MOSFETs, IGBTs, and other control circuits, and then that is used for passing the energy into a storage device. There are many different types of storage devices. One can choose from chemical storage like the battery, where the electrical energy is converted to chemical and then retrieved using electrochemical means. You could store it as a hydro storage. The electrical energy is converted, it lifts water to a height and stores as potential energy of the lifted water. It's called the pumped hydro. You can retrieve the energy with the help of a water turbine. You can also store this electrical energy as compressed air. So it can drive a compressor and compress the air to different levels of pressures, and you can retrieve it with the help of an air turbine. Or you can store it as mechanical kinetic energy in the form of a rotating flywheel and retrieve it by means of an electric generator. The solar energy gets converted to electric energy at the PV module, and this electric energy is stored in one of the various storage mechanisms through the energy charger. Alternately, the energy can also be routed directly to some load. The energy can also be routed from the storage mechanism into the load through a bidirectional energy charger. So these paths lead to a power electronic device which does the job of conversion, power conversion to an appropriate form which is compatible to the applications. The power conversion can be a converter, which means it gives you a DC output, or it could be a power inverter which gives an AC output to drive applications that are either DC or AC respectively. The inverter outputs should have AC loads, the converter outputs will have DC loads. A sample set of loads would be something like lighting, for LED lighting, fluorescent lighting. It could be pumping to pump water up to a height and store as potential energy. The pumps could be DC pumps or AC pumps. You could have refrigeration, the regular compressor based refrigeration, which is an AC load. You could also have DC refrigeration by means of using Peltier junctions, which are very compatible to the PV type of source. You can have grid connection. This is a very upcoming type of application where the photovoltaic power, after getting converted into AC through a grid connected inverter, gets pumped into the grid, where any load that is connected to the utility grid can also be served. So this is one of the application which is emerging as one of popular applications for PV systems in the smart grid scenario. Now what you should note is that MPPT, maximum power point tracker, is a very important term that you will be seeing more and more in the lessons to come or the discussions to come. All the power converters and the energy converters must incorporate maximum power point tracker. What it basically means is that the PV module has a power versus V characteristic which has a peak at one operating point only, and it is recommended that the PV module operates at that peak power operating point so that you can get the maximum out of the PV cells. So it is the job of the power conversion unit, the power converters or the energy charger units, to see that appropriately a load is presented to the PV module such that this will operate at maximum power point. So these maximum power point tracking algorithms should be inbuilt and should become inherent part of these power converters. So these are some of the sample, some of the important components that you will see in the solar PV systems. Now we have three important components here. Of course, MPPT is part of these two, which we need to study and also design so that we can implement these kind of components for any solar PV system. First, let us take up the sizing of the PV module. Sizing of the PV module is very important because it occupies a lot of real estate, and real estate doesn't come cheap, and therefore you need to give a lot of thought into this. Unfortunately, this has a lot of dependency on the local geography, the incident radiation coming from the sun, the atmospheric condition, water vapor content, the latitude, time of the day, time of the year. All these parameters affect the effective energy that is coming out of the PV module. So it is very, very important to study this PV module in connection with the local geography and the local latitude. Consider a PV panel which has these outputs. It is taking the input from the sun and it has an input of P in. This is the power, and the output power P naught. And recall that efficiency is given by P naught by P in. And this is equal to Vm Im, which is the voltage and the current corresponding to the operating point on the IV characteristic of the PV panel, divided by P in is nothing but the incident insolation into the area. The insolation is having units of kilowatt per, this is having a unit of kilowatt per meter square, this is in meter square, so this would become the input power. Now what is this A and the insolation L? Now if you consider a panel drawn like this, then this area as seen here, on the flat plate solar PV panel, that is the area A in meter square. Consider a normal passing through this area, and let us say that the solar radiation is falling in this fashion at an angle theta as shown. This is the angle theta like this. So what you should consider is actually the normal incidence. So if this is called Li, then what you should consider for the PV panel calculation is Li cos theta, which would be the normal incidence. So what is effectively converted as power is the incident insolation normally on the flat plate panel. So this will become Li cos theta. So now replacing, you will see that Li cos theta is the effective insolation that is given to the panel. Therefore, the efficiency becomes Vm by Li cos theta into A. Therefore, P naught is equal to Vm and this is equal to, if I take these two components, efficiency into Li cos theta into A. So you see that P naught is dependent on the area of the collector and Li cos theta, which is the incident insolation normal to the collector. P naught is dependent on the application. The application will tell how much load power is needed, and this is the amount of electrical power output the panel has to give. So P naught is a requirement. Efficiency is from the data sheet of the PV panel. Li cos theta is the incident insolation in kilowatt per meter square, and area is the size of the collector panel plate that has to be exposed to the solar energy in order to collect enough energy to provide this P naught. So we need actually to find out what is the value of A in order to size and select the PV panel. So if you rewrite this equation, A is equal to P naught by efficiency into Li cos theta. So you see that area of the panel is proportional to P naught and also inversely proportional to the incident insolation. So at a given place, if the insolation is high, then the area of the panel that you need to select and choose for that place can be lower. And likewise, more the load power, higher should be the area of the panel. So we see that both the load power is dependent on the incident insolation, and also the area of the panel that we need to choose is also dependent on the incident insolation. However, it is not easy to find out what this incident insolation is because it is dependent on very many factors. It is dependent on the time of the day, it is dependent on the time of the year, it is dependent upon the local climatic conditions, it is dependent on the water vapor content in the vertical column of the air above the collector, it is dependent on seasons. So like this, it is dependent on so many factors, and many of the factors are uncertain. It is not easy to estimate the incident insolation. But our objective now is to go towards finding as accurate a value of the incident insolation as possible so that we may be able to size the panel, size the collector area for a given load power requirement.